So now we know that benzene reacts completely differently than something like cyclohexene, that these double bonds are not normal alkene double bonds, they're aromatic double bonds. Well, in the next set of podcasts, we have to look at how benzene reacts. It reacts via a substitution reaction rather than an addition reaction. And the cool thing about the next few podcasts is how it ties all the concepts together: mechanisms, carbocations, and resonance. So get ready to draw lots of hexagons, and we'll try to understand how benzene reacts. So instead of addition, benzene reacts via substitution. It's like a double replacement reaction. So we're going to take bromine and add FeBr3 as our Lewis acid catalyst. Remember, Lewis acids are a species that will attract electrons, and we have a lot of electrons in this benzene ring, even those electrons are very stable as an aromatic ring. So when we run this reaction, we're going to do a substitution reaction. As I said before, there's an H here. In fact, there's H's all around this benzene ring. Well, one of those H's is going to be lost and be substituted by one of the bromines, and then you make HBr in the process. Now, it's a three-step mechanism, but the 3 steps include the first step, which is the reaction of the bromine with the Lewis acid catalyst. Bromine has a fairly weak bond, and then it will be, the electrons in the bond will be attracted to the Lewis acid. So the first step in the process is creating a bromonium ion, which is not very stable, but it is stabilized by the presence of FeBr4- right next door. This is our electrophile. In every single reaction that we're going to do of electrophilic aromatic substitution, we have to first generate an electrophile, because the electrophile is what attracts the electrons from the benzene ring. So our first step is to generate an electrophile with our Lewis acid catalyst. The second step is actually what we call the rate determining step. For the most part, it's the slowest step. It's the hardest reaction to happen because we have a very stable benzene ring here. But this is what's going to happen, is one of those pi bonds is going to break and attack this bromonium ion. In the process, what you get is you've lost the aromaticity, and we now have an H and a Br on this carbon here. We still have a H on this carbon. It's always been there, generating a high energy intermediate, the carbocation right here. Now, the last step is going downhill to regenerate that aromaticity. And what I usually do is I draw it coming from this FeBr4-, and these electrons in the hydrogen-carbon bond end up making the pi bond right here, and we complete the substitution reaction. Now, in the process, this structure right here will break up into HBr and FeBr3. We just regenerated both the aromaticity and the catalyst. So if we look at our 3 steps, our first step is generating the electrophile. The second step is the electrophilic attack on the benzene ring, losing the aromaticity. And the third step is losing the H+ to regenerate the aromaticity. So here's step 2, and here's step 3. And all the mechanisms of electrophilic aromatic substitution follow these 3 steps. The only difference is the electrophile that you form in the first place. Now, if you look at these 3 steps of the reaction according to energy and the reaction coordinate. What we're going to do is look, the first step, it's got a fairly high activation energy. Goes like that, and that's the beginning. That's the generating of the electrophile. The next step is the rate determining step, or RDS. So this will be the highest hill. And right here is our carbocation intermediate. So I'm just going to draw right here, put a general electrophile, and I'll put a plus right there to indicate our high energy intermediate. And the last step will be completely downhill because we're going to get back that 150 kilojoules of energy for aromaticity. Well, that was sort of ugly, but that'll work. So if you look, here is where we generate our electrophile. Here is the rate determining step, and here is regenerating, making our product. So why is this important? This actually tells us where our rate determining step is. And because of that, anything that will lower this hill will allow the reaction to go forward in a different path. And we're going to learn how different substituents on the ring will make this path be either steeper or less steep. And it will allow us to predict where substituents or electrophiles will add to the ring. So there are multiple different electrophilic aromatic substitution reactions, all that follow that same mechanism. If I had put the benzene ring in the middle, the first one we did was bromine with an FeBr3 catalyst to make bromobenzene. Correspondingly, we can add a chlorine atom with chlorine and FeCl3 to make chlorobenzene. Now, if I take, this is sort of nasty, concentrated nitric acid in H2SO4, both of which are concentrated, what's going to happen is I am going to add a nitro group to the ring. So I make nitrobenzene. This is important for explosives. If I just add H2SO4, sulfuric acid, to the ring, I will make a compound that looks like this. I add SO3H, which is called benzene sulfonic acid. And then there are two ways to add carbon to the ring. The first one is adding carbon as an acyl group, something like this. The Lewis acid we use is AlCl3, or anything that will generate a carbocation will work. And you will get acetophenone by adding that acetyl group to the ring. And the last one is adding just an R group rather than an alkyl group, rather than an acyl group. The R group has to be stabilized because it's very difficult to make a primary carbocation. So by stabilized, we're going to add T-butyl chloride to the ring, which is a stabilized carbocation, and you end up with T-butyl benzene. These last two reactions are name reactions. They're called Friedel-Crafts, acylation, and alkylation. Now, the different electrophiles for all of these look like this. For bromination, you add Br+. For chlorination, you add Cl+. For nitration, you add NO2+. When you look at the Lewis structure, it looks like this, with the plus on the N. For making the sulfonic acid group, it's SO3H+. And again, the plus is the one is on the sulfur. And so this is what benzene sulfonic acid, the electrophile, looks like. And for acylation, it will be this structure right here, which is stabilized by resonance. It shouldn't be bent, but we're going to just leave it bent. And then, of course, the electrophile with the T-butyl group is T-butyl carbocation.